here we go. So Advent on Code Day 4, giant squid. I love the theming of this year. The water theme's cool. You're already almost at 1.5 kilometers, almost a mile. That's good to know. Below the surface of the ocean, already so deep that you can't see any sunlight. What you can see, however, is a giant squid that has attached itself to the outside of your submarine. Doesn't sound good. Doesn't sound good. Okay. Bingo has played... Maybe it wants to play bingo. So bingo is played in a set of boards, each consisting of a 5x5 grid of numbers. Numbers are chosen at random, and the chosen number is marked on all boards on which it appears. Numbers may not appear on all boards. If all numbers in a row or column of any board are marked, then that board wins. The submarine has a bingo subsystem to help passengers, currently you and the giant squid, pass the time. It automatically generates a random order at which to draw numbers in a random set of boards, your puzzle input. So for example, okay. Oh boy. So right off the bat, this is going to be more complicated to pass than any of the other examples so far. We're going to have to do some fiddling with this, right? So it looks like this is like a sequence of numbers and then a bingo card. So the first 5 numbers are drawn. There are no winners, but the boards are marked as followed. Oof. So this feels like it might even be like a state monad, right? Like we're gonna have a collection of boards. We're gonna change the state of these boards, like update these boards. How are we gonna represent this? Am I gonna regret Haskell? Maybe. But oh boy, we are gonna have fun trying. Okay, so marks things out. Next week numbers. There are still no winners. The third board wins because it has at least one complete row or column of marked numbers. Cool. So the score of the winning board can be calculated. Awesome. This is really cool, actually. I love this way of encoding the responses, I guess, or encoding the answers in like the outputs of things. Okay, so step 1 is to actually model this, right? And when I look at these in Haskell, the first thing I like to do is to imagine what our data is going to look like. So let's go to the simple thing, right? So let's say we have a card. So a card, it's going to be, let's not even do like Haskell syntax, right? A card, it's going to be a grid, a series of rows. How do we encode these rows? Let's do the simplest thing for now and say it's, and these are hard coded at 5x5, right? 5x5 grid. Okay, so let's say it's a list of row where a row is a list of something. It's kind of got to be a pair, right? It's going to be like a number, which is, you know, the actual value in the card. So like this cell would be 11, but then it'll also have like maybe a bool for if that number's been called or not. Does that make sense? I guess it does. So then every time a number is called, we can update a card by looping over each okay. I guess, yeah, iterating over each row and then finding rows that have matching first elements and then updating the second. Or I guess a tuple is a bad thing for this, right? Like a cell is probably just like a cell int bool, right? So there are a few things we're going to need to be able to do. So we're going to need to be able to call a number, right? So call is going to take a list of cards. It's going to take the number that we're calling, and it's going to give us back a new list of cards. Let's forget the state monad. Let's forget anything fancy like this. Let's just do the simplest thing we can for now, okay? So the idea is that we're going to have this call function, go over our cards, and it's going to update the this kind of boolean bit from false to true if this number matches the thing in the cell. And then we're going to need a function to like check if a card has won. So let's say check. That's going to take a card, and it's going to give us back a bool. So check will be for, yeah, like has an entire row or column of this card been marked by this operation. So we're not going to worry about the IO bit first, right? We're just going to make sure we can actually represent the problem and write the functions that will allow us to solve it. So let's go solve Okay, and so we can just represent this pretty directly in Haskell, right? So we'll start with a cell. Data cell int bool. And let's make a utility function for just like making a cell in the default state, which is going to be false. Maybe this is a bit ugly, I don't know. I don't hate this. I don't hate this. So we need a row. A row is going to be a list of cells, and we know it's going to be 5 long, but we're not, like, we can't actually encode that. Well, I guess we could. I mean, I guess we could actually say row, cell, 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 cell. Is this a little bit... let's try this. You know what? Let's try this, because I think it'll be easier to check if a card is complete or not like this. Maybe, potentially. And then a table is going to be table, row, 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 row. Right? 5 cells in a row, 5 rows in a table. But what am I doing? What am I doing? Data row equals, and then data table equals, beautiful. Let's pull up. Oh, am I gonna, is my face in the way here? Maybe. We'll see if I need to move this around. Let's go. Cool. So we're gonna keep a GHCI instance running here so we can kind of poke this stuff. So let's start with a really simple function. Let's say mark. This is going to be our function where... Oh, I called it cool, didn't I? Cool. It takes a number. It takes a list of tables. Hold on, let's call these cards. They're cards, okay? So it takes a list of cards. It takes a number. And it gives us back a list of cards. A list of cards single. Okay, so cool n equals. Cool, sorry. We're going to do this recursively as well, because of course. So our base case is going to be when there's an empty list. Cool. Okay, so cool, if we have a card, what do we want to do with it? We want to try and update each row. So I guess this is where the hard part comes in, right? We would love to be able to map a function inside the structure, like turn it into I guess like a really crappy functor almost. Oof. What if I just do that? What if I just do this really like... No, but this is the only thing we need to do inside of it. Okay, I'm overcomplicating it. What we need to do for each row, do the same thing, right? So we're gonna have a function called, yeah, because this card. Oh wait, no, hold on. Wait, so this card, right? It's card row 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 row. So let's do, okay. So we're gonna have some special cool function which takes the card or the card and does something with it. Okay. This looks weird, but it's gonna make more sense once I get to the next line. This is good. And then call CSN. Let's swap the arguments around so this actually lines up. Okay. Because now, like, the thing with doing this as a data type rather than a list, right? We need to destruct this somehow into these 5 rows. We can do this fairly elegantly. I think I can say we're cool card R1, R2, R3, R4, R5 equals, right? I think I can destruct it like this. But then what does this actually equal? That's the question. So we need to do like a similar thing, right? We need to update a cell. Equals update cell. Oh, well it equals. When we really need some kind of function to like do this. What if I say... What if I say this, right? What if I say update cell... Well, no, yeah. What if I say update row? Okay. Okay. We can update a row, right? We can update a row. We can take a function that maps between two cells. And then we can take a row and we can give back a row, right? So... So let's say update row... And then we want to say update card. Right? We can do the same thing on like a bigger scale. And then we want a function that can turn a function from cell to cell into a function from row to row. Okay, how about that? How about that? So maybe I should draw some pictures of this. I don't know. It's still taking shape in my mind. This is going to get clearer as we go. This is going to get clearer as we go. Okay. But I guess the what I'm getting caught up on right now is like trying to make this look nice, trying to make this feel nice. But I think I'm onto something here. Okay, so what if I say do to row? Okay, so this is going to take a function from a cell to a cell and give us back a function between two rows. Okay, is this insane? Is this crazy? Perhaps. But the idea is that we can say right down here. The idea is we'll say, cool. We'll probably even simplify this, right? We'll get a new card equals update card do to row, right? So we take a cell in, right? So cell let's say mark do to row mark match and let's imagine a function called mark match for a second, okay? And then this will just take our card. Easy, that simple, right? So this mark match is gonna have to look something like, right? So this is a function between two cells. Mark match cell n anything equals if hold on, this has to take an int as well. Cool. So this is a function that takes an int and then gives us back a function from a cell to a cell, right? So and that's fine. If I equals n, right? So if the number we take in and the value of this cell are equal, then we give back cell n true, else. Man, this chunky terminal is gonna be the end of us. Okay, else we give back cell n false. Okay. Does this make sense? Maybe not. I think this is a fairly elegant way of representing this, right? We get the fixed widthness. So then the only thing missing from this is do to row. So do to row f, and then we take a row. So let's unbracket that, I guess, so that we can say row C1, C2, C3, C4, C5, right? And this is just equal to row FC1, FC2, FC3, FC4, FC5. So we've kind of implemented, this tastes like a functor, right? This feels a little bit like a functor, but it's like a crappy, very specific functor that only does what, It's not a functor. It's something that looks like a functor and smells like a functor, but it is really just like restricted down to the absolute bare minimum that we need it to do. Okay. So does this work, right? Probably not. Update row lacks accompanying binding. Update row, update card. Oh yeah, of course. That checks out. Update card, due to row. Update row actually, funnily enough, is like no longer. So row to row. Wait, due to row. Gives us back. Wait, update card takes a function between two rows. Update row takes a make match due to yeah. Okay. let's just do this. These became the same function. These somehow became the same function. I guess we just call this up? Let's just call it doodle row, that's fine. And then update card is gonna basically be the same thing, right? Update card F card R1, R2, R3, R4, R5 equals card F R1 F R2 F R3 F R4 F R5. Let's rename this. Let's rename this to update row. Maybe this makes sense. I mean, it looks okay. So let's go. What's a good way to make? How do we construct this? So let's just do it a dumb way. So let's go row, cell 1, cell 2, cell 3, cell 4, cell 5. R2 equals row cell 1. Let's just duplicate this, right? I guess that's easier. Oh, there's got to be a better way of constructing these things, but anyway. I guess I should put this in the file so that I have a good testing thing to work with, maybe with some better numbers as well. Okay, so then we go card equals card, R1, R2, R3, R4, R5, card. We don't have a show instance, of course. We should probably do that. Do I have to wrap these in brackets? I can never remember. What if I load? Load, solve. Yeah. It's just parentheses, right? Yeah, perfect. Okay, deriving EQ show and deriving EQ show. And then let's put like a test card in here somewhere. So let's go test card cell 1, cell 2, cell 3, cell 4, cell 5. Is Haskell going to let me do this with white space? I'm not sure. Three cell 4 cell 5 5. Can I do this? I bet this complains. Mismatched. Okay, it doesn't like that in a new line, but that seems pretty good now actually. Perfect. So let's go test card. Test card equals card. Test rows 0, test rows 1, test rows 2, test rows 3, test rows 4. And if I load test card, nice. The formatting's disgusting, but we've got a card. We've got a card that's going to do stuff. So if I say call card, let's say the number 1. Variable not in scope card. Yes, that's because it's called test card. And it looks like the cells that have the value 1 have been updated to true and the cells that don't have remained false. So this works. This was a bit of a confusing nightmare, but it works. Cool. So all we did was, yeah, write functions that let us apply an operation to the whole structure very easily. And one that can actually be chained together in a cute way, right? Like update row, we have a function between 2 cells, we take in a row, we give you a new row. But you can also think of this as taking in a function between 2 cells and then giving us back a function between 2 rows, which we can then pass into a function that essentially does the same thing just for a card. So this is messy, this is a bit ugly, there's probably a much smarter way to do this, but we haven't had to use the word monad, and we've got something that works. That's all you can ask for in Haskell. That's all you can ask for in Haskell 101, okay? This is pretty nice. These names kind of bother me a bit, but this is a solid recursive way to do this. I like the where clause here. I think that makes a lot of sense. Mark match is a pretty clean function. You know, it's just an if. I guess we could also put that here, potentially, right? Rather than like... But it has to be a function is the only thing. So yeah, I guess we could also say where mark match cell n blah equals if n equals, well, let's call this like maybe I now, and say if n equals I, then cell n true, otherwise let's change this to I, because this is the one that's actually in the cell. It's going to look confusing if we use n's, and we can't give back n here because this is the actual one we're marking and it doesn't match and blah blah blah. So what if I do this instead, right? Does this a little bit nicer? This a little bit cleaner? Ooh, not a fan. Not a fan. Oh, because we're giving an argument here where we don't need to. Nice. Okay, so we can do the same thing, right? We can call test card 1, we can call test card 2. We're going to see the cell 2s are updated. And now these things don't carry over, right? We're not mutating anything. So if we want to apply this multiple times, right, you'll have to say call this. So we can chain these together, right? So now we've called number 3 and then called number 2. We can see these have not chained together. Interesting. Okay. I'm glad we tested that. I'm glad we tested that, because that was going to blow up in my face. What's going wrong here? How has this... What has... Cool... So this gives us back this. Oh, hold on. Hold on. We're actually marking things that don't match as false. What we want to do is give back whatever boolean was already in it. Okay, so now if we reload this... True. Yeah, cool. Okay. Bug found, bug solved. This is why REPLs are so good. This is why REPL languages, REPL-based development is going to change your life. Okay. It's huge. It's huge. So, this is great. This is great. This is coming together. Okay. So we can mark bingo cards. We need to be able to check to see if something wins. This is going to be the hard part. Okay, so let's say... let's make a function. We're going to call it check, as I have in my wonderful plan. Check. It's going to take in a card and give us back a boolean. Okay, so check card R1, R2, R3, R4, R5. Maybe regretting this structure now a little bit more. Equals. So So we want to say, let's say row found or col found or diag found. It's going to be either any of these 3 conditions where row found equals, right? So row found is going to be true if one of our rows are all marked. So this is going to be the most simple one to implement, right? So if it's going to be all true or row equals This is where it might be good to actually have a functor, right? Because if we could just map over a row and go from a row of cells to just a row of bools, then we could just fold over that. And if every bool was true, then the row matches, right? Like that's kind of, oof. Oh, it's kind of what we want though, isn't it? It's kind of what we want. Do I just make this a func? Do I make this, okay, here's what we do, Oh man, hold on, whoa. I'm a little bit in the way here, aren't I? Hold on. Yeah. Okay, hold on. Whoa. Let's get me front and center where I belong. Okay. Can't keep me out of the spotlight if you tried. Okay, there we go. All right, we're back in it. So row found. Yeah. So what I want to be able to say is, right? I want to be able to say fold L or fold R, fold L. And, right? So I want to say fold R and I guess I don't need like a functor, right? I just need a function which takes a cell and gives me back a bool, right? So but then if it's a row of bools, but then I need to implement fold on it as well. Okay, so I'm fighting myself here, right? On one hand I've got higher things. So what's going to happen here, okay? So we're going to have check equals row or col or diag, right? So is there a row, is there a column, is there a diagonal? And then we can treat these things completely separately. It may not be the most efficient way to do it, but it's good. So if we have R1 ... R5, right? A row is true, and then a row is just cell 1 through cell 5, right? So row n equals, let's say row test R1. So a row is so there is a row found if any of the rows pass our test, or ... and then this test is going to be are all of our cells true? So C1 and C2, and we'll just treat them as booleans for now. So rows are easy. We just go straight across. We compare all of the cells in the row. A column's a little bit harder because we have to say R1 C1 and R2 C1 and ... And then a diagonal is just going to be, well, there are only 2 possible diagonals, right? Because the other diagonals aren't 5 long. So it's just R1 C1 R2 C2. So maybe a list was actually the right structure, right? Because pulling all this stuff apart by hand is actually proving to be a bit of a pain. It's okay. We'll be fine. We'll be fine. So row, let's say row found equals. Oh, I just want this to be clean. I just want this to be beautiful. I guess I could like destruct all of these rows as well, right? And just have a horrible, horrible, messy table of awfulness. Row found. Test R2 or test row R4, right? So let's be verbose. Let's be verbose. I think I'm missing something simple, right? But let's just be verbose. Test row R5. Okay. Col found equals. Now this one's going to be harder. Col found equals. Is there a way to not just write this out and make it horrible? Column found. Maybe I can't do this with a where clause. Okay. So row is simple. Row is simple. Column is hard. How do I represent this? Maybe this is easier with lists. Maybe this is just better. Maybe my life is better with lists. Or maybe I can like maybe I can like just do something really silly like this, right? Like maybe that will make it easier because then I can I don't know. There's no because okay. I've tried to be too smart. So what I need to do is go back and rewrite this with lists, otherwise this is going to be unreadable soup. So here's what we do. Data cell. Cell is fine. We're going to keep the cell. But then a row, I think we just change this to type, right? Or data type. I've got to Google this stuff as I go. Type alias. Use type and not new type. But I want this to be a new type. I want this to be treated. So new type. But instead of this horrible thing, we're just going to say a row is a list of cells and a card is a list of rows. But actually we want all the listy stuff to come along with it. So let's just call it a normal type. Okay. So update card and update row are now irrelevant. We have a functor instance, so we can do more interesting stuff. List of card. Okay. So update card. So now this is actually just, so we have a function from one cell to another cell. So this looks like, right? So cool. So we want, so we've got a list of cell, and we want to go to a list of cell, where some function f, has been applied to every cell, right? For all C. Does that make sense? Maybe not. So we want to apply this function to everything here, right? So we can, if we fmap over this, we fmap, like we can, so let's say, yeah, fmap A to B, FA, FB, right? This doesn't quite work for the list of list, but if we chain two fmaps together, we can take a function from A to B and do it like inside of the double list. I don't know, maybe that's a bad explanation, but we should be able to say So if I go t fmap of fmap, yeah, that's what I saw before. And let's just fill this in with some default values. And then we need to update this as well. So you're now just a list. Cool. Oh, and this is now actually just a card, right? Test card. Yeah, this really cleans everything up a lot. Hey, we're relying on existing structures. I like it. Okay, it's a little bit ugly, right? Because we need some commas. Make match? Yeah, mark match. Nice. And so if I do this again, check test card 3. Couldn't match type cell with cell. In expression test card, expected row actual card. Check. Oh, sorry, yeah. So check, blah, blah, blah. That's. What I meant was call test card 3. And it looks like the cells with the 3 are marked true and the other ones aren't. And then I can go call test card 4. So the 3s and the 4s should be true, everything else is false. Okay. Isn't that a lot cleaner? Isn't that a lot better? We can just like leverage this functor to great effect. Okay, so row found now. We can do this much better. We can do this much better. So now we can pull out our friend, the right fold. We can fold and. So t folder, right? So we can do this better. We can do this way, 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 way better. Let's get this. I need a harder eraser. God, this eraser is pathetic. I need to change my like dynamics settings. This is no good. Okay. Now we can do this really, really smart. We can do this really smart. I know being overly smart was what or trying to be overly smart, but this time we're just actually going to be smart, right? Okay. True. And then we take. Okay, so. So a card is a list of rows. And a row is now just a list of cells. So we want to know. So let's say we have R1, right? List of cell. Wouldn't it be much more interesting if this was just a list of bool? And we can do this with another fmap. You know, we just like we would just say lambda x goes to I think second x, right? Because in this case our x is going to be some integer. Oh wait, no, I didn't use a tuple, did I? X goes to. I actually don't know how we would destruct this most effectively here, right? We have. Can I destruct on this side of the lambda binding? Can I just say like, so if I say lambda x goes to 4. What if I say lambda cell n b? Yeah, cool. Okay, so I can destruct on the left-hand side of the thing. That's very, very good. So now instead of so I can say cell, right? I can make a function that takes in a cell and just gives me back the Boolean value for that cell. So I can map that over a list of cells and get back a list of bools. And then I just do a fold, right? I take the Booleans and I collapse them down into a single value with a fold R. And because I want this to be true when they're all true, I use logical AND, right? And my unit for this, for the logical AND, is true. That has to be it, right? That has to be it. And fold R true, and then we take this is what we were saying. We need to fold. So let's say lambda. Let's say fmap lambda cell b goes to b, and then we map that over. Yeah, there we go. We map that over the rows. So a row. Wait, no, hold on. I'm one level too deep. So this works out, but this is for an individual row. So we need to do this for each row. So this is row found prime, I guess. Where we're just doing this for an individual row. Row found equals, so row found, right? We have a list of row. And this is going to take us from a row to a Boolean. So what we could actually do is the same thing, right? Fold R, except this time we're going to fold OR, because if any of the rows match, then it matches. We're going to fold R false, fmap row found prime. Okay, let's see what happens when we load this. It's probably going to yell at me. Or not. Check test card. Cool. So what if I go x equals... Well, actually, hold on. Let's write a function that's going to call several things. So let's say call list. It's going to take a list of cards. It's going to take a list of ints. And then it's going to give us back a list of cards, right? So call list cs empty list equals cs, and call list cs x xs equals call cs x followed by the recursive thing, right? Just some good old-fashioned recursive list building. Call list cs x's. Expected. So with cell, second argument of this call gives us back a list of cards. This gives, this gives us back a list of, what do I want? Oh yeah, hold on, no, I don't want to append, do I? I want to call x. I want to call this on the result of this, right? So let's call, and this is why, again, like maybe a state monad is an interesting idea, but call list, we have our cards and we've got the numbers that we're calling, A, B, C, ... Right, and this is basically just going to expand out into a bunch of calls. So we're going to say call cards A, or no, yeah, we're going to say call cards C, B, A, right? So this is our first call. This gives us back a list of cards, right? Cards where the number C has been called. And then this is going to treat, this is going to take that new list and call the number B on it. And then this is all going to come down to a list of cards. and then we're going to call the number A on it, and then this is all going to come down into our final list of cards, right? Perfect. So actually, maybe it's worth swapping the arguments around here. Cool. Right, and eventually this is going to hit the base case where it just gives back the original list we pass in. So if I load this, cool list, test card 1, 2, 3, 4, 5. Everything should be Oh, hold on. Yeah, we take a list of cards. Perfect. Everything's true. So now if I check this before I wreck this, oh yeah, blah, blah, blah. Yeah, of course. Cool. So check is returning true for this. That's interesting. What I would like to do now is to come in and actually make more interesting values here, right? So 6, 7, 8, 9, oh no, 10, 11. There's got to be a faster way to do this, especially the ones where you're just adding a tens column, but whatever. 11, 12, 13, 14, 15, 16, 17, 18. Now that these are, now that this is just a list, again, I can actually do this a much less manual way, but whatever. 20, 24, 25. Cool. So reload it. And now this is still going to say true. What if I say 1, 2, 3, 4, 6? It's going to say false. Nice. I'm going to say 8. So cool. So this looks like it works. And I'm fairly confident it works because we're just folding. We're just, these are all well understood operations, right? The column's going to look pretty similar. So let's do the same thing. Let's fold false. Let's do this or. So like if any col found, if any column is found, col found C equals. So in our column, wait, hold on, no, that doesn't work, does it? Because we don't have a nice little column object, do we? We can't Fmap over anything. The columns are more complicated. But I guess we kind of want to do this over a list, right? So we're going to have a list of check col 0, check col 1, check col 2, check col 3, check col 4, right? Where check col n. So if we check column 0, right? So we, in the first row, okay, this is coming together. Equals check col n rs. Okay. So what we're gonna say, right? We're gonna have this recursive function. It's gonna go through each. Wait. Does this work? Yeah. So when we check a column, we do this recursive thing. This recursive thing has a base case of false because we're gonna... Wait, no, it has a base case of true because we're ANDing things together. Okay, hold on. Right, but what we want to do, we want to check a column. We want to do this. So when we check col 0, we want to take the... For each row, we want to take like the 0th, or like let's say the first element, right? So we want to say R0. Let cell B equals R0 in B. In B and check call nrs. Okay, so we're destructing the cell from the, except this is going to be the, rather than just hard coding it to the 0th index. So we're getting the nth thing in the row, we're destructing it to get the Boolean value, and then we're ANDing it with this recursive call, which is eventually going to go down to this base case of true. So if they're all true, this is going to come out as true, and if there's any false, this will come out as false. So can I build it? I can. And when I call this, it's going to say false. So what if I say, right? What if I say 1, 6, 11, 16, 21? Comes out as true. Oh boy. And if I just like tweak this a little, oh, this is exciting. This is exciting. Let's try a different one. Let's try the right hand one, right? Just to make sure there's nothing like weird at the edges. 5, 10, 15, 20, 25. True. I love it. Okay. So now it's just the hard one, the diagonal one, right? And we can actually just kind of say diag1 or diag2, I guess, right? Diag1 equals. Diagonal 1 is the one where the first index. Oh, Tilful with the raid. Thank you so much. Man, Tilful, how you going? It's been ages. It's been ages. We're doing some nerd coding. We've gone fully down the nerd rabbit hole into Haskell advent of code. It's amazing. It's amazing. Welcome, everyone. Welcome. Hope everyone's having a wonderful night. Man, yeah, I moved to New Zealand. Holy crap. How did that go? It must be a really weird time to move. But that's awesome. It feels like home. I'm definitely finding Melbourne feels like home now, right? Like I look into the city and the buildings are familiar and it's good. It's good. You can feel your brain shrinking looking at this. Haskell looks intimidating, but it's kind of beautiful. It's kind of beautiful how elegant some of these... Oh, man. Wow. Don't know if you can hear that, but that is a fire engine on my street. Cool. Okay, we're not stopping to here. That's good. Managed to move just before the bubble closed. Man, my cousin just moved back from New Zealand to Australia, and so he came in to Melbourne. He had to do a week of hotel quarantine in Melbourne, and now he's flying from Melbourne to SA, and he has to do an additional 2 weeks of hotel quarantine in SA, which is like ridiculous. Ruben, SG1234, thank you very much for the follow, by the way. Yeah, it's super crazy time. Super crazy time. Okay. So we're checking a diagonal, right? So we're playing bingo with a giant squid. This is just how advent of code goes. It's beautiful. So we need to check. We need to know if we're hitting a diagonal, and this is the hard one to check, right? Diagonals are hit. Okay, diagonals hit. Let's go. So if 0, 0, 1, 1, 2, 2, right? We kind of like. We walk down the line. So we can do this in like a really clever one-line Haskell way, or we can do it a dumb way. I'm leaning more towards the dumb way right now. For each. Let's go the dumb way. Let's go the dumb way first. Okay, so let's say. Let's write a little helper function for this. Let's call it get. It's going to take an int, it's going to take an int, it's going to take a list of A, and it's going to give us back an A, right? And it's going to be extremely unsafe. Let's call them x and y equals x, y, t, t, x, y. Don't do this. Don't do this. Really not a good Haskell idiom, but it's okay. So get 0, 0. We need to do our Fmap as well, don't we? So let's say bt equals Fmap of Fmap cell b code's fun. Code is really fun. It's good. I think a lot of people get like a bit intimidated by it or a bit put off by it. There are really like fun ways to learn code. This is not one of them. But yeah, like if there's anyone watching who's like a little bit interested in code, who's played with it before, Advent of Code is a really cool, fairly low pressure way to experiment with some problems. You know, if you've got time over Christmas, you want to look at them. Some of them get a bit involved. Like the first day, I think, is a good learning problem if you want to like try a new programming language or something. These ones, this is fairly standard stuff if you've seen like coding interview questions a lot. But yeah, like they start to get tricky. Like this is taking me a fair while to beat my head through. But it's so satisfying when it comes together, and Haskell's a really cool language because you get to do things in a very mathematical way, and like if that kind of thing appeals to you, if you like drawing out pages of how the data flows through and whatever, it's cool. Okay, so we're gonna convert these into true and false, and that's gonna be good. We can do that. And then we just need to give it arrows, and then so this is going to give us a true or false, right? So diagonal. So if the top left thing and the like 1 1 and then 2 2 and get 3 3 and get 4 4. Let's just say diagonal 2 is true. So let's see if this builds. And I can't believe that these things are just building out the gate for me so much. I'm having really like a really good run with this. So if I check this, let's do an example that shouldn't pass. Yeah, okay. So this, wait, 1 6. Hold on. So here's our table, right? So 1 6 11 16 19. That's not being. Oh, hold on. This should be false. Okay. Because that is not bingo. That's not how bingo works. 1 6 11 16 19. That's not bingo. False. Okay, good. So now if I say 1 7 13 19 25, this should give me a bingo. 1 7 19. What did I say? 1 7 9 13 19 25. And that does it. And if I change it to like 24, it's going to say false. So that's awesome. And now I can just basically copy this, right? Except instead of 0 0 1 1 2 2 3 3 4 4, I do the opposite. I go 0 5 1 4 3 3. So 0 5 1 4 2. Wait, 2 3. Wait, hold on. I missed something here. Oh, I missed something because I start at 4, not 5. There we go. 3 2 2 3 4 3 0 4 3 2 1. Yeah. Cool. 0. Okay. Love it. Does this work? Does this just work? Okay, I can simplify this again if I actually pull this up and use this definition, but okay. Okay, not quite. Because I didn't change the name. Alright, I love it. So let's just test this other diagonal. I really should have written a better test system of this, but anyway, 21 17. Okay, 21 17 13 9 5. 17 13 9 5, and that passes. Okay, so we can play bingo, we can simulate bingo. Now we just need to actually read in the problem and do the I/O, and that's the only thing missing. And so there are really good ways and really clean ways to do this in Haskell, and I'm not very good at any of them. Let's actually grab my puzzle input, right? Cool. So this is a bit meatier than the example one. Let's start with the example one. I'm just going to copy and paste this into a file. That is not what I meant to press. Copy. Let's go test. Cool. Okay. So main equals. We want to read this. Do we want to read this line by line, or do we want to just say like input is read file test lines let in. So the first line is gonna be the numbers that we're gonna taken. So we've got to kind of deal with these separately, and then we write something for the rest of the lines, which are going to be these like chunks of 25 numbers. And I guess it's well-behaved input, right? We don't have to... One of the great things with Advent of Code is all of your inputs are well-behaved. They're nice numbers. They're well-structured. They're not going to throw a weird curveball at you. So you can just make some really good assumptions. Like I don't have to worry about there being one too many numbers in this input. I can just say everything's going to come in nice chunks of 25 numbers. I can probably just throw it into a Haskell function called words, maybe. So I can call words on each line and then concatenate everything together, right? So we get this input. We're thinking about an input in lines, right? So this first line, and then other lines will have stuff on them. So line 0, this is it's a list of numbers that are separated by commas. So we'll do something special for this. And then the rest of the lines from here, right? We want to take whatever's in them. So let's imagine it's like A, B, C, and we want to turn that into a list A, B, C. And there's a Haskell function that does that. So we can I guess this is a kind of confusing way to write it, right? But basically we're going to end up, with like, each line is going to turn into a list of characters, and then we can just mush all of these lists together with the rest of the lines. Everything except this 0th line. So we kind of handle this separately, and then everything else here is kind of easy. So we can do this. Let's go tail. So let's say this first line, let's call it sec, because it's the sequence of numbers that can get called in the bingo game, and then we're going to say cards equals tail, right? So everything else in. So now to get the cards, right? So like I said, so we're gonna map a function. We're gonna map words over the actual card data, right? And then we're gonna concatenate all of the numbers together, and then we're gonna read them as integers. We're gonna like read internally, right? So we're gonna convert like the number 2 into the actual number 2. Okay. This is good. This is coming together. But then we need to do something with this. So there are two functions. There's take, t take, and there's t drop, right? So take 5, 1, 2, 3, 4, 5, 6, 7, 8, and then drop 5, 1, 2, 3, 4, 5, 6, 7, 8. So take 5 gives us the first 5 elements, right? And drop 5 gives us everything after the first 5 elements. So what we can do is kind of recursively call these two functions, right? We can take 25, that'll give us our first card, and then we can drop 25, and that'll give us either a list with at least 25 elements or an empty list. We know this because our input's well behaved. So what's the best way to represent this? Let's go make cards. It's going to be a function that takes a list of integers and it gives us back a list of cards, right? So make cards empty list equals empty list. Make cards x's equals. So we have some numbers. We want Is there like a take drop function that does both these in one, like gives you back? Anyway, no. Because the nested list, this is a bit awkward, right? So we want... So this is a card, right? 5 rows makes up a card. And then this is joined on with make cards drop 25 X's, right? So now we just need where R1 equals R2 equals, we need to actually define what these things are, right? But this is what the function's going to look like. We make a card, and then we call make card on the next 25 numbers. And eventually we'll get an empty list, and hopefully this will never like blow up, and we'll never end up with an invalid card. Everything's going to be beautiful. Everything's going to be beautiful. So, I mean, I guess you can do this, right? You can say, we can fmap, because we've got this function cell that makes a cell in our table, and it just takes a number and gives us back a cell. So we can fmap cell over take 5 X's, right? And then we can do the same thing for the second row, but we can go fmap cell take 5 drop 5 X's, right? So this is the first 5 things, then the next 5 things, and then we can just duplicate this a few times. Except now instead of drop 5, we go drop 10, drop 15, drop 20, right? So we jump over more and more things. And this works. This should build, right? The types check out in my head. Okay, the types don't quite check out. Oh, because I didn't actually do anything with this. Yeah, that's good, that's good. So we call make cards with it, right? And let's just say print make cards. Can I just print things up? What type does print have? Yeah, perfect. Okay. Pass error in word in. Make cards. Yep, cool. Few things missing. So, folder, second argument of namely. Let's do away with this fancy fmap shorthand. I think that's going to be better. Fmap, read this thing. Oh, hold on, yeah. Well, first off, I suspect this is not bracketed enough. I don't think I have enough brackets. Yeah, perfect. So the problem was it was kind of like taking this as one thing and then trying to... Who even knows? We're taking each line and converting it into words, into like things that are separated by spaces. We're mushing them all together. We're reading them into numbers, and then we're turning those numbers into cards. So if I go, well, I guess I just like, that's interesting. Okay, this looks like we've passed a card. That's good. Maybe I'll just print out the first card that we grab, and I'll check that against... Oh, I've got to reload. So 22. So if I go over to test, so 22, 13, 17, 11, 0, 8, 2, 23, 4, 24. Yep. 21, 9, 14, 16, 7, 6, 10, 3, 18, 5, 1, 12, 20, 15, 19. Perfect. I think it's safe to say this works, right? We can pass things in. That's cool. Okay, so we've read our cards in. Now we just need to convert this first line into a list of numbers, which we can then pass into cool list, right? So we've got our list of cards now. That's what we get in. Let's call this, maybe let's call this card or let's call it raw cards, right? This is the cards before we've refined it into our nice high quality representation. So we'll call this cards, and then we'll let's say call numbers equals, and we're gonna do a fairly similar thing here, I think. So if we check our input again, right? So these are tightly split apart by this comma. So we can just say, right? So split 1, 2, 3, 4, right? Or not? T split T. What's it called? What's it called when you split a string in Haskell? What's the Haskell string split? Do I have to import something, or is this surely? Split at. Is this in? Oh wait, no, but this takes a number. Okay, so what I want a function. So for people who haven't used Haskell before, Hoogle, fantastic resource, because I can imagine the type signature of a function. So I can say a function, a list of things that takes a thing and then gives us back a list of things, right? Split list, beautiful. Split on, that's good. Split, what is it? X monad, that's not quite right. I just want this in the standard library. Where can I get you? Where can I get this? Wow, is there really no option for this? Chop. Lines and words corresponding to new line. Show the standard word is split on a comma. You can let definition of prelude functions. Word. Oh, there we go. Okay. Okay, so this is kind of good, right? Mimicking. Hi, how you going? We are losing our minds looking at Haskell right now. Apparently, we're doing advent of code, right? Really cool problem. Playing bingo with the giant squid. I love it. Fantastic theme this year. Apparently, Haskell doesn't have a standard library way to split strings at a character, which is awesome. But Stack Overflow to the rescue. Stack Overflow to the rescue, as always. As always. Cool. So just modifying the standard words function to actually take this with a predicate. So what we do here instead, we say where we had words before, Stack Overflow. I do not know where I would be in my career without Stack Overflow. Man, when I worked in an identity and management team and just had no idea what I was doing, absolute lifesaver. Absolute lifesaver. And yeah, this year, in the last 6 months, I've kind of learnt Golang on the job. And man, the amount of Stack Overflow browsing I've had to do, it's great. I love it. All right, so we need to do the same thing here, right? We need to do the same thing. We're gonna words when. All right, we don't need, except instead of checking for a space, we're just gonna check to see if it's a comma. We're gonna map this over. No, we're not. We're just gonna throw this at the one line. Stack Overflow got you through your advanced diploma, man. What's your advanced diploma in? Words when sec. So this is gonna give us, and then we need to do our read on it, right? Cool. So this gives us our list of numbers, and we don't need to tell it what we're actually reading, right? This is one of the cool things about Haskell. Read doesn't give us back a specific type. It's just like a generic function. But if we then use this cool numbers in a way where it has to be with a list of ints, which we're gonna do, we're gonna pass this what is technically just a generic list into a function that expects a list of int, and then Haskell will work backwards and decide that they have to be read as ints. Professional game dev, that's awesome. That's really cool, man. Man, I can't even imagine what an advanced diploma of game dev would look like, but that's awesome. Man, I imagine like a lot of vector math and oh man, I don't know if you watched my streams when I was doing like the early PS2 dev streams when I was just going crazy about 3D camera stuff. Oh, you did that at AI in Melbourne. That's cool. That's cool. I didn't know you were a local. Man, you watched it all. Thank you. Yeah, a lot of game dev stuff I have like some pretty big gaps on, right? I've joined a Discord lately with some guys, which was cool, and they just like talk about game dev stuff, and I'm absorbing more knowledge. They seem to know a lot more about like rendering and stuff. So I'm sure as I get into more interesting PS2 things with like, you know, bone-based animation and whatever, I'm gonna have a lot of questions for him. Cool. So we've got the numbers, we've got the stuff. Okay, so now let's print the actual answer. Let's calculate the answer. So what we do, we've got this really cool function. We already wrote it. We already tested it works. Cool list of cards, list of numbers. It's gonna call the numbers in our bingo game, right? So cool list. Except we only call hold on. This isn't as simple as I thought. Okay, so we've got this function call list, which is really cool. It's really useful. Call list, right? List of cards, list of ints. It gives us back a list of cards. This was great for testing, but the problem with the actual solution for this is kind of like we don't keep going. We only want to find the first thing that wins. The first card that calling check on that card gives us back true. So this isn't as simple as I thought. What we can say instead, I guess we can have like a modified version of this. So get winner, and again, this assumes that a card wins. But I think we can assume that because advent of code gives us very nice input. So if we take a list of cards, we take a list of numbers to call, this will actually just give us back a single card, the first card that wins. So call list CS. If we call it with an empty list, then something's gone wrong. No winner. And that's probably an error in our logic. Sorry, get winner. I got distracted about what I was typing there. Get winner. Our cards, we have x excess equals. So if so then we kind of want this shape, right? We want to, if we have a winner, then give back the winner. Otherwise do this recursively until we find a winner. So where 1 equals, well, actually, first things first, let's say where suck equals, the successor to this state, right? The successor is call CSX. We call the number on our cards. 1 is we want to check all of these cards, and we can fold over this, right? We can Fmap over this. Yeah, we can fold an Fmap. So we can fold R, or false, right? So this is what we're doing before. So we check if any of these things are true, but we do it in a very Haskell-y way. Fmap, check, suck. Beautiful. So this says, did anything win? Your advanced diploma was basically writing 3D graphics in OpenGL, 2D physics library. Man. Nice, you did marching cubes, VR with Unity, and a major project where you actually make a game. That sounds really good and practical. I talk to people around Melbourne especially, and it sounds like when they do programming stuff at uni, they get a lot more practical experience than I did at poor old Adelaide Uni. Yeah, it's really weird. Like, so much of my degree was so theoretical, and so many people, it felt, came out of my degree with no real experience or knowledge of how to actually like write programs that did stuff. The only reason I have experience writing programs is because I just did it in my spare time because I loved doing it while I was at uni. Like, my degree did not prepare me for the real world. Not to throw too much shade at Adelaide Uni, right? There are some really fantastic staff there, but on the whole, I think the program felt a little bit outdated, like more on the theoretical side of computer science, maybe, if you wanted to like stay and be a researcher. But yeah, most people are just going through into the industry, and it wasn't the best. They did actually start to overhaul it in my last year, but of course that's too late for me. So the hardest thing about this, I think now, so we've got this condition for if we've won, right? This is great. I love this. This is beautiful. But how do we actually get the winner? This is where I think we need some short-circuiting logic, right? So do we just, for now, let's accept we're gonna call check twice potentially on everything, right? Equals if one, then get winner. Let's make this a function, right? So rather than having this pre-calculated, we'll say get win as a function. I guess it's lazy anyway, right? That doesn't matter. It's the same thing, right? So Haskell's lazy. So if this doesn't evaluate to true, this won't be calculated, right? Haskell won't do it unless it needs to. So we can actually be a little bit inefficient here. If winner, then we want to find, does it say what happens if multiple things win? Lindsay has the one complete row of numbers. Score of the winning board can be calculated, blah, blah, blah. Okay. Which will win first? Yeah, so the way this is worded implies that only one board will win. Which is fine. So the winner's the first board. So let's do this recursive thing again. That's fine. Winner blah CS. Oh, let's go x's equals if check x then x else winner xs, right? So we do this recursively. The first one that is true, we return. Winner, and if we get to the end, checking for winner that does not exist. Okay, so now this probably won't load. I'm sure I've done something wrong. And of course it's indentation. Thank you. We're Python now, boys. What have I done? One? Yeah, because it's the wrong indentation. So if I come out here, or mismatched brackets, that's more compelling to me. That feels more. Where have I gone astray? Check x and x. This all looks good. Nothing's escaping here. Nothing's leaking here. Oh no. Oh no. Is there a good tool that's going to give me a better error message than this? Possibly incorrect indentation. Possibly incorrect, right? That's not a message. I can't do anything with that. I can't do anything with possibly incorrect indentation. Come on. Oh, doesn't that ruin your day? I'm ready to solve this. But it is not ready to be solved. Possibly incorrect indentation. It's got to be this where not being in the right spot, right? Can I just like do this? Is this gonna pass error? All my other wheres were like this, weren't they? All my other wheres were like this. Oh, this is it's just stumbling at the 11th hour. Okay, what if I just like get rid of things and see at what point it starts working? Actually miserable. I hate it. I hate it. And this is just gonna... Oh, hold on. Okay, that's actually really good, right? That's really, really good. So is it this? Wait, did I miss paste? Have I... Oh. Well, that explains it. Okay. This is actually my bad. Let's say print get winner cards. Get winner cards call numbers. So that was failing because this in was dangling at the end of the file. So again, why don't I get a better error message? But whatever, that's fine. So apparently this is the winning card. Now, do we see true? Oh, I can't read this. This is true. This is true. So it must be the second to last. Nope. False, true, false, false, true, true, false, false, false. Okay, let's write this out. So we've got an answer. It says F, false, true, false, true. This one says, this row is false, 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 true, false. Now, unless there's a whole row that are true, which it doesn't look like there are, I don't think this is a winning bingo card. False, false, true, false, 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 true, false, false, true. Oh no, it's the diagonal. It's the reverse diagonal. It's actually there. True, false, 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 true. Holy crap. That works. And so then the answer should be... oh wait, hold on, no, but we need the last number that was called. Crap. So what do we do? How do we calculate the one complete? Start by finding the sum of all unmarked numbers on the board. Multiply that sum by the number that was just called. Okay, so what we actually need, get winner. It's got to give us back a card and the number. Then winner is this. Winner is then wait, no, then oh, sorry, bumped the thing. Then winner X, right? Because X is the number that we just called. So if I call solve, it's going to give us back the number 2. But this looks like it's not. Yeah, this is the thing. But the number 2 wasn't just... What? I'm going crazy. Complete row. Wait. Did it not say diagonals? Did I not read this very carefully? It shows another mark on the board. I swear I read diagonal. That's... Okay, there's actually no diagonals. I'm actually overcomplicating my life. That doesn't sound like me at all. So let's just comment these out for a sec. And say diag found equals false. Okay. So now if we solve, that looks correct. That looks correct. Wow. I did all that diagonal work for nothing. Beautiful. Okay, so we go let C I equals get winner cards call numbers in print so the sum of the numbers. So we've got a list of lists. Okay, now there's a really good Haskell way to do this, right? We've got a list of cell, right? We want to go to a number. So what do we do in the middle to do this, right? What goes here? First things first, we can map this into a list of int, right? The cell structure is just going to be awkward to work with. Let's just make them numbers. We know how to work with numbers, okay? Then we want to just turn this into one big list of numbers. So we've got to go from list of numbers just to int, right? And we can do this. We can join these things together. We can fold. I think there's a function that actually does it, right? Concat. Yeah, so if I say concat 1, 2, 3, 4, I should get 1, 2, 3, 4. Perfect. Okay, so this is a function called concat. This exists in the standard library. Concat. This is an fmap. Right? So then we concat it together, and then we just call sum. There's a function called sum to get our final int, right? Sum. Sum. Beautiful. Okay, so it's that simple. Print. So we want to say, what did I just say? So we fmap lambda cell I whatever goes to I. I could just sum of sum. Can I just sum of sum? Dagley, thank you. So sum of sum. Oh, I can just sum of sum. Holy crap, because sum. Yeah. Oh, that's good. That's good. Thank you. I really appreciate that. Because like I think I've got an fmap of fmap up here, right? Yeah. So like I've been thinking like this, but sum of sum, that's good. I don't know. This code, okay, this one got away from me a bit. This one got a little bit out of control. There's probably a much nicer way to do this, but we're just gonna live with what I got, right? Advent of code's about learning, not about oh boy. So I do need to get this into a list, right? So fmap this cards C, and then we just sum of sum this. Then we multiply by I. 120 lines, it gets replaced into 4 lines. That feels like my Haskell experience in a nutshell. Okay, so I did something weird. I feel like this is like an order of operations thing, right? Like if I wrap this in an extra bracket, it might be okay. Okay, not quite. Can't match type cell with cell. Expected cell actual. Oh yeah, because I need to literally I was just talking about this. I need to fmap of fmap it. But again, I think maybe this is like grouping not the way I want it to, right? What happened here? Sure, let's see what happens. Okay. No instance num int arising from use of sum. Sum of sum. Wait, so what type is sum of sum? Num. Foldable number. Yeah, so that's fine. So I've done something, in conclusion, I've done something weird again. FAB. So this is a mapping between a cell and a number. And this is a list of, hold on, what have I, no, that, I literally used this earlier, right? I literally used this earlier. I think I need to write this potentially just on more lines. Okay, let's go. So a cell, we just go down to the number, and then we convert our card just into a list of numbers. And then we sum it. This at the very least should give us a better error message, right? Print. Forgot the word in, that's fine. As ints, okay. Try using the $ more. Yeah, I always struggle with the $ when I'm, like, I can do $ and I can do dot, but when I start mixing the two, I really lose track of where I am, right? That's one of my shortcomings, I think. Like for sure, like just not really getting the operator precedence, really. Like I look at this and I'm like, I assume this is gonna do this first, but I actually don't know. Right? I actually don't know. Okay, so first argument to this to multiply sum as int. Second argument of, so this is grouping like I think it does. Couldn't match type. Expected type. So, but this doesn't bloody. See, the annoying thing about this as well, right? It does. I now have none of this loaded in my interactive session. So let's just like do this so I can poke it. Oh no, it's not gonna. That's annoying. As ints. Okay, couldn't match type cell with cell. Expected cell, actual card. Yeah, so a card is a list of cell. Fmap. But so. Okay, hold on. Whoa. A card is a list of rows. A row is a list of cells. Oh, but we've just got one card. Oh no, but a card is a list of rows. A row is a list of cells. So if we fmap, we get a list of cells. If we fmap, we get. What is? Oh, I've done something odd. What a place to limp over the finish line. Everything else is working beautifully. Second argument f, namely. So it's telling me, right? It's telling me second argument fmap in C. C is a card. C is a card. Expected list of cells got card. Okay, so what it's telling me is it looking at this? It looks like it's telling me that it's trying to just apply this, like, just at one level, right? Rather than... Let me just try putting a bracket around it. Or that? No, that makes less sense, because that applies the whole right-hand side first. No. I was so confident. With this picture. Okay. Let's take a step back. So, solve gives me an answer, right? Yeah, hold on. That just prints. Can I? Cool. So C is a card. Let's go cell I blah goes to I C. We can't do it. Okay. Okay. It has applied to too many arguments. Second I'm gonna dot. Yeah, so this is this saying it's not grouping the way I want it to? Maybe. Yeah. So that's what I want. That's what I want. So I guess, so if you're still around, Dagley, is there a way I can use a $sign to like clean this up, or is this just bracket soup? Because I swear I've seen people do this more cleanly. I swear I have done this more cleanly. Fmap of Fmap. Like, oh no, I did bracket it up here. Okay, okay. So let's go. Fmap of Fmap. I blah. Just turn it into a number. And then return as ints. Okay, so this is good. This is good. And then let's see if we can sum it. No. Sum. No instance for sum arising from use. Does it, what, it expects the list event to have the, Okay, look, what I'm gonna do, something weird's happened. I'm gonna say sum. I'm just gonna do this. I'm just gonna do this. And that works. And that gives me an answer. Does that give me the right answer? No, because I need to multiply this by I. And that's still the wrong answer. Because... yeah, the $sign just binds loosely. Yeah, awesome. That's not what I want. That's, yeah. Because if I have a $sign here, yeah, it'll like try to apply this to everything to the right of it, right? Like, a $sign basically just has the lowest operator precedence, and yeah, it does nothing. Okay, so we're adding up the card, we're multiplying it by I. Something has gone bad. I think my sum was wrong, right? 325, 188. Yeah. Oh boy. But this is the... Where are marked numbers? Okay, let's start by finding the sum of... Oh, all unmarked numbers. Yep, that would do it. That would do it. So now we can just filter, right? So we can say... where are we? Filter... right. So we're gonna filter out. We're only gonna. Oh no, hold on. We want to keep. Is there a? There's a not in the. Yeah, cool. So we only want to keep things that are unmarked. And that has not quite done it. So let's unmarked let's split it out onto another line. I'm finding it easier to juggle. Filter, cell, blah. Right, so we take a cell, we give back a bool, and then that is C. Unmarked. Unmarked, countermeasured with F of cell. Filter. C is a cut. Oh wait, hold on. Okay, what we actually need to do first. Okay, here's what we do. We're gonna mush this together first, right? Then we're gonna Fmap it just once. Because the filter is easier once they're mashed together, okay? That makes sense. So now if I solve this, I just get the numbers. Yeah, so there's no 14, there's no 21, there's no 17, blah, 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 blah. So now if I were to do the sum of this, so let's say x, solve, sum of x. Oh, right, sorry, I'm printing it out, I'm not returning it anymore. Where are we? So now if I grab this, I say sum x, I get 188, which is the answer. Cool. So let's just go print as ints sum as ints times I. Now if I load this in, I solve one more time, we should see the number 4512 like we expected. So now I'm going to change this to the actual puzzle input. Again, like this is a janky way of rigging up a test harness, but we'll be fine. Did I save this already? I don't think I did. Yeah, let's go input. Let's go CP temp. Cool. So see if this is that magic number. I'm so excited. That's the right answer. First time every time. Easy question. Part 2, on the other hand, it might be wise to try a different strategy. Let the giant squid win. You aren't sure how many bingo boards a giant squid could play at once, so rather than waste time counting its arms, the safe thing to do is to figure out which board will win last and choose that one. Oof. That way, no matter which board it picks, it will win for sure. So in the above example, the second board is the last to win, which happens after 13. Okay. So to find the last board that wins, we want to filter out any boards. So this is easy, right? The way we've rigged this up, this is really easy. So first things, let's go git add yeah, I don't want these, right? What's the, oh man, I always forget this. Get on stage. I always forget how to do this, right? How to do this without blowing the files up. That's not. Nah, screw it. I'm just gonna delete them. Cool, so solve one. Okay, so get winner. Right, we kind of do this like recursive stuff to work out the first card that wins. Get loser is going to look very similar. And then, the second board is last to win, blah, blah, blah. And then we do the calculation the same way. Okay, so get loser first things first, no loser. If we run out of numbers to call, and we haven't found the loser already, we aren't going to find the loser. It's a malformed input, and that shouldn't be the case. Get loser. Okay, so if get loser. So if we have one card followed by nothing, then we always give back that card, right? That card has lost. That is the last card standing, but we can't do it here. We can't actually check that recursively because we need to know the last number called as well. Okay, so xs equals if then so what we're going to say is if we determine that we've found a loser, we've found the last card, then we just return the only card that will be in that list. Otherwise, we do this recursively for our successor state and for the next number that's called. Except, again, we need to actually give back the number that was called. And in this case, it's x, right? Where our successor state is the result of calling this number x, right? So this is, you know, like the next round of being, the next number's been called. And then we're going to say, we're going to filter out cards that win. So is there a standard library way to filter but like the inverse? There must be. There must be like a cleaner way to do this. Anyway. Cool. So no winners, right? Anyone who wins, you're out. You're out. Actually, let's call this like suck prime. Sure. Sure. I don't know. Messy names. So if you win, you're out. We don't want you. And then we know there's a loser. Loser equals length suck equals 1, right? We know we found a loser when we only have one thing left. I actually think that's the only... I actually think that's it. I think that's all we need to check, right? I think we can just mash these things together. And I can just come in here instead of this, say, get loser. Did I cover everything there? Oh, I need to bloody resave the input. Sure. Oh, and I only copied, so I could have just done that before. Okay, so we're gonna copy. We're gonna solve. I don't think this is right, but let's see. Yeah, too high. That feels like it's way too high. Okay, so let's just have a quick think about this, right? So, I mean, I don't know how it gets a number this high, first of all. Let's go back to return as ints. Yeah, weird. Let's go xi. I guess that's a kind of big number. Okay, so card with So we're not finding the loser correctly. If loser, then our loser condition's good. Our loser condition is so good. Our filter, maybe not good. We're saying that yeah, we want things that don't pass. Like once you pass this check, you're gone. Once you pass that thing, you're gone. Yeah, so we only keep things where this is true. And this is only true if you're not, if you haven't had bingo. So all the cards that don't have bingo, we're definitely doing the right successor. We filter this down. What am I missing? What am I missing? What am I missing here? So we call the numbers on the bingo card. We find all the cards that are not in bingo, and then we check the length of that. If the length is 1, then we're done. We've found the losing card. There can be no worse bingo card in our set. Let me double check I'm doing this right. Last one, no. In for example, the second board is completely right. If you keep playing to this point, the second board would have a sum of unmarked numbers for a final score. Yeah, so the same calculation method. It's annoying. That's annoying, and it definitely wasn't 15,799. No, it's too high. It's too high. Please wait 1 minute before trying again. Okay. Oh, that way now I know which board it picks. It will win for sure. It just feels like this is the right way to go. What number was called? 61. So if I go into the input, where's 61? Pretty near the end. That seems likely, right? That seems pretty likely. And then my board, so let's look for the number 66, right? So 66, 45? No, 45. 66, 45. There's a 45 here. There's a 6 here. No, there's not. 45? 45? No, 45. 45, 6. This must be the board, right? 60, 65, 17. Cool. I mean, I can't just like verify it by hand, I guess. This is too many numbers. I'm gonna have combinatorial explosion. Like if I try and look at how all of the, I guess, yeah, but there's only one path. It can't be that hard to verify. This is probably actually doable by hand, right? So what has gone wrong? Because everything else worked, right? Everything else appears to be working well. What if I do this slightly differently recursively? This shouldn't make a difference, right? This should give us exactly the same answer. But if it somehow doesn't, that's a good indicator that something's gone foul. And it gives the same answer, okay? Second board is the last to win. Well, okay, yeah, hold on. Let's do this on our test input. Right? So let's go. Okay. So if we go. Yeah, and so we can just see outright that that's wrong, right? So 13 should be the last number called. I'm saying the last number called is 16. 13. So I'm 1 too early. Ooh, that's interesting, right? So the sum is 148. So if I go sum x, I get too many. 13. Hold on. 161 minus 148. That's 13. Oh, I'm stopping one number too soon. I'm literally just stopping one number too soon. Oh, okay, this is solvable. This is crackable. I've got to go to bed, but this is crackable. Oh, I can do it. I can do it. Okay. One number too soon. I'm stopping one number too soon. Why? I guess I just have to go one further, right? What if I just do the stupid thing, right? And I just say head of excess. What if I just do this? This is going to give me the right answer for the wrong reason, but it'll be okay. Sum x 100 Because I'm still... No, I've got to simulate one more step. If the length... But why, like... 13 is good and its middle column is eventually marked. Oh, yep. Oh no. I accidentally toggled my colors. Okay. Yes. Sorry. So, it's not when this length is 1, it's when that card wins. So we've got the loser, right? So then we need to find the number that makes that loser win. Get winning number. Let's say loser. The loser. Get winning number. The loser. Okay, so what we need a way to step through and calculate what the winning number for a given card will be. So let's say get winning number. Okay, it takes a card, it takes a number, and it gives us back a number. So get winning number. It takes a list of numbers. Sorry. C blah equals. That's bad. If we run out of numbers, it's a malformed input. Get winning number card x x's equals. So where if 1 then x else get winning number c xs, right? So it's this recursive pattern we've seen a bunch of times here, right? If we win, then we give back the number that made us win, otherwise we keep going. Where 1 equals, except we're going to call this c prime, right? So where c prime equals call c x, and then 1, we win if check c prime. Okay, here we go. Can't match type cell with cell. Oh, yep, cool. Head C prime. Wait, no, hold on, I'm wrong here, aren't I? Cool? Yeah, no, cool does work on a list of cards. I'm right. Okay. Head C prime. Very not in scope of the loser, yep. So the loser equals head suck. Okay, now if I say solve, I should get the right answer, right? I get the number 13 back. Okay, so let's go down, let's go input. And let's solve this bad boy. Hold on, I wanna, let's go print sum as ints times I. Let's see what happens. Oh, still the wrong answer. Okay. Oh dear. 66. So when I call 66, when I call 66. Oh, hold on, because 66 shouldn't be called. So, I feel like if I remove 66 squared from this number, so like if I have 17094 minus 66 times 66, I'm thinking this is going to be the final answer, right? 23738. I think I just need to check this number off the card, right? So the loser. Let's keep going down this track. Let's say winning no equals get winning number the loser xs, and then let's say true. Oh wait, no, but this, we need all the things checked off, right? We need all the things checked off. Oh no. So this is now just going to have a more complicated return type, right? So instead of just returning X, we're going to give back this is fine. This is fine. Cool. So then I come down here. I go print sum as ints times I. Yep, that's what I said it would be, because maths. But you can't solve these things with maths, right? You have to solve them with code, and there we go. This was not my finest attempt. Okay, the leaderboard is not my friend. I was hoping to get maybe number 4 and number 5 smashed out today. I'm gonna have to go to bed. This has turned into quite a stream, quite a meaty stream. Let's have a quick read of day 5 as well, because I don't want to get too far behind here. So hydrothermal venture. Okay. You come across a field of hydrothermal vents on the ocean floor. These vents constantly produce large, opaque clouds, so it would be best to avoid them if possible. They tend to form in lines. The submarine provides a list of nearby lines of vents. Okay, so this is some real like state stuff, right? We've got like some kind of grid. We're kind of, line drawing algorithms. According to the other end, these line segments include the points at both ends. Cool. Discrete. I love it. Only consider horizontal and vertical lines. Okay. Yeah, so this is going to be really fun to try and do in Haskell. I don't really know what my approach would look like, right? A lot of spin in your wheels, I think, to do this just with like a list of lists, but also probably the nicest way. You can probably do a lot of cool stuff with like lazy evaluation. Anyway, that is a problem for another day. This has been Advent of Code Day 4, done in a very roundabout and very slow way with a lot of really dumb issues, but honestly, end of the day, apart from the fact that I tried to check diagonals when that was actually unnecessary, I think this was kind of cute. I think this was kind of clean. Also, I actually just overrode my solution to the first part. Crap, hold on. Well, I can fix that anyway. But yeah, that was really fun. That was good. I'm really happy this worked. This parsing logic is kind of messy. I can do this a lot cleaner if I really wanted, but it works out well. I like that we have like get loser and get winner. Again, I don't actually need to split this out into 2 parts. I can just change the get loser to get winner. And this is what I like about these Haskell solutions to these problems. It's usually just like you can add a few bits to your pipeline or change a few bits in your pipeline. This get winning numbers thing ended up a bit messier than I wanted, but this is pretty clean. This is pretty nice. It all just like fits together, right? The gears just fit together. So before I say too much, thank you very much for tuning in. I need to get to bed. Advent of Code, it's really fun. Give it a crack. I'm Tom, and I'll catch you next time.